In 1944, the skies over Europe are basically a conveyor belt of Allied bombers. Germany is running out of time, running out of fuel, and running out of pilots. And then, something flashes past the camera that doesn't look like anything else in the war. No propeller, two engines hanging under the wings, and a sound that's less airplane and more industrial scream. This is the Messerschmitt Me-262, often called the world's first operational jet fighter. And here's the secret: it wasn't just advanced, it was compromised on purpose. Because the Me-262 wasn't engineered for perfection. It was engineered for a collapsing empire that needed a miracle it could still afford. And that trade-off is where this story gets weird. By the time the Me-262 becomes operational, Germany is under relentless air attack. Aircraft factories are being hit, engine plants are being hit, rail lines are being hit. Everything needed to build modern machines is getting erased from the map. So the requirement isn't build the best fighter. The requirement is build something fast enough to intercept bombers, using an industrial system that's falling apart. That's why the Me-262's story is as much about manufacturing as it is about aerodynamics. Production gets dispersed into smaller, harder-to-target facilities, sometimes essentially improvised sites, because big, centralized factories are too easy to bomb. And that decision echoes through everything: the airframe layout, the materials, even the cockpit details. No two late-war aircraft are perfectly identical, because the war is actively smashing the supply chain while you're building the plane. So the Me-262 becomes a kind of distributed engineering project. Not elegant, not consistent, but survivable, at least on paper. From the outside, the Me-262 looks sleek, but the secret isn't sleek. The secret is manufacturable. Its fuselage shape is basically a practical compromise, smooth enough for low drag, simple enough for fast production. Internally, it's a familiar framework of longerons and stringers tied together by formers. Think of it like a skeletal cage that's easy to assemble in sections. Then comes the wartime reality: materials. In an ideal world, you want lightweight alloys everywhere. But wartime isn't an ideal world. Critical materials become scarce, so designers substitute wherever they can, sometimes using heavier steel in places that would normally be aluminum, trading performance for availability. And some non-structural parts can be simplified even further: covers, panels, secondary elements, because the goal isn't beauty. The goal is output. This is also where decentralized production matters. If your plane is being assembled across multiple sites, your design must tolerate variation. That's why you'll see differences in small fittings, panels, and layouts between airframes. It's not sloppy engineering. It's engineering that expects disruption. The Me-262's wings have a swept leading edge. Today, sweep screams high speed. But here's the twist. On the Me-262, that sweep wasn't a magic supersonic upgrade. It was tied to balance and design evolution as the aircraft's weight and center of gravity realities shifted. Then you get the features that make the jet survivable at lower speeds, because jets aren't just fast, they're also tricky when they're slow. Automatic leading-edge slats help prevent stalls at high angles of attack. Flaps increase lift for takeoff and landing. And there's a very smart anti-pilot error idea baked in: systems that reduce the chance you configure the aircraft dangerously. Because the Me-262 has one humiliating weakness: it's most vulnerable when it's slow, on takeoff and landing, exactly when Allied fighters learn to hunt it. This isn't a jet age problem, it's a This jet is being born in wartime chaos problem. If the Me-262 is the headline, the Junkers Jumo 004 is the plot twist. It's often described as the first mass-produced operational turbojet engine, and it uses an axial flow compressor layout that's basically the ancestor of most modern jet engines. Air enters the intake, gets squeezed by multiple compressor stages, fuel burns in combustion chambers, and hot gas spins a turbine. Part of that turbine power keeps the compressor turning. The rest leaves the nozzle as thrust. Simple concept, brutal execution. Because Germany can't reliably build high-temperature turbine blades with the best alloys by late war. That forces compromises in materials, and the engine pays the price. One widely cited consequence, the 004B's service life can be shockingly short, often measured in tens of hours, not hundreds. It also has fragile throttle behavior. Early turbojets can punish you for moving the throttle too fast. Dump fuel in before airflow catches up, temperatures spike, and turbine blades suffer. So pilots are taught something that feels ridiculous in a fighter. Be gentle with the throttle. Then there's startup. Instead of a modern electric system, many early jets use external carts or clever internal starters. The 004 can be started with a small, two-stroke gasoline starter motor design. Basically, a tiny engine whose job is to wake up the big engine. So yes, the Me-262 is fast, but its speed is riding on engines that are brilliant, delicate, and, by necessity, disposable. That's the secret engineering. A jet fighter designed around an engine the wartime economy can barely support. Now arm it. The Me-262's most famous fighter setup mounts four 30mm Mk108 cannons in the nose. This weapon is built for one job: killing heavy bombers. It throws big shells at a high rate of fire, often sighted around 650 rounds per minute, but with lower muzzle velocity than you'd want for long-range precision. So Me-262 attacks tend to be close, fast, and violent. Short windows where a burst can do catastrophic damage. Then you get rockets. Some Me-262s carry underwing rockets like the R-4M, designed to let pilots fire from farther out and disrupt tight formations. Less sniper shot, more shotgun blast into a box of bombers. Fuel is the other constraint. Early jets drink fuel fast, and Germany's fuel situation is already dire. So the plane is built for quick climbs, quick interceptions, and then back home. Because loitering in a jet in 1944 is a luxury nobody can afford. Let's do this from the pilot's seat, because this is where the Me-262 stops being a cool machine and becomes a job you might not survive. You climb in, strap down. The cockpit is busy but logical. Flight instruments clustered in front, engine controls given a lot of space, because with early jets, engine management is life. First rule, don't rush. You bring electrical systems online. You check fuel selection. And when you start the engine, you're not turning a key. You're initiating a sequence: starter engaged, engine spools up, ignition, and then a careful rise in RPM. Move the throttle too aggressively and you can overtemp the engine. That's not a theoretical risk. That's a "your turbine blades are now a sad memory" risk. Now you taxi. Takeoff is the danger zone. The Me-262 is fast in the air, but on the runway, it's a target. Allied pilots learned to hunt jets here, diving on them when they're heavy, slow, and committed. If you get airborne, the world changes. You climb hard, build speed, and approach bomber formations with tactics designed for closing speeds that piston fighters never had to manage. A typical attack isn't a slow tail chase. It's geometry. You set up from above or behind. You manage speed so you don't blow past the firing window. You fire short, brutal bursts, and then you extend away. Because your advantage isn't turning. Your advantage is leaving. Then the clock starts ticking. Fuel, engine health, and the trip back to the most dangerous phase again. Landing. So why doesn't the ME-262 win the war? Because engineering doesn't exist in a vacuum. Yes, it's terrifyingly fast. Yes, it's heavily armed. But operational reality is cruel. Production is disrupted. Logistics are collapsing. Trained pilots are scarce. Airfields are attacked. Fuel is limited. And engines have reliability issues driven by material shortages and design compromises. And even if around 1,430 were built, a commonly cited total, only a fraction are combat-ready at any given time. Jets need maintenance. Early jets need more maintenance, and the ME-262 is most vulnerable exactly when it's least able to defend itself, takeoff and landing. So the aircraft becomes a preview of the future, trapped inside the constraints of the present. The ME-262 didn't change the outcome of World War II, but it changed aviation. Underwing engine nacelles, axial flow turbojets, high-speed aerodynamic thinking. This is the DNA of the jet age, showing up early, imperfect, and under impossible conditions. The secret engineering of the ME-262 isn't just it was advanced, it's that it was engineered to be buildable in a world that was actively collapsing, and it still flew faster than anything the Allies had in the sky. If you could walk around one system on the ME-262, engine, guns, wings, or cockpit, what would you want to see modeled and labeled next? If you enjoyed this kind of inside the machine breakdown, like and subscribe for more engineering-focused history. Thanks for watching.